The objective of this presentation is not about the Riemann integration. The objective is the visualization of differentiation of standard functions. Riemann rectangular strips can give the visualization of differentiation of standard functions. So when we do the Riemann integration, for our case, we have to focus on this question. These rectangular triangles. So when we find the slope, so this becomes delta y, this becomes delta x. Similarly, this becomes delta y, this becomes delta x. For all these cases, we find that delta x is same and delta y is different. So here delta y is different, here delta y is different, here delta y is different. So focusing on delta y, it will give us the information about the slope of the function. So this will help us to visualize the slope of the function, that is differentiation of the function. In the Riemann rectangular strips, already we have seen that delta x is constant within the limit of integration. Delta y varies as a function of dy by dx. So here we can see that the delta y is varying. So the value of delta y is different for different points of the curve. And we can find that delta y, it is representative of dy by dx for each Riemann subdivision. The variation of delta y, it represents the differentiation of the function under consideration. It is very important to note that the function dy by dx is exact only if delta x tends to 0, as shown in this corresponding curve. But we are not interested in calculation of dy by dx in the exact manner. Our motive is to visualize the differentiation for learning purpose. For visualization, this is acceptable. Come, let us go for visualization. First, we will discuss about the case of polynomial integration. Any polynomial can be represented in the form of ax power n. We are going to discuss about the differentiation of polynomials. And for this case, the equation is y is equal to k, that is y is constant. The differentiation of a constant is 0. The next case is y is equal to x. The differentiation of that is 1. And the next case is y is equal to kx, linear. The differentiation of y is equal to kx is k, which is constant. And the next case is the polynomial case, that is y is equal to ax power n, or x power n if a is equal to 1. So the differentiation is nx power n minus 1. So that is what we are going to discuss. First, we will discuss the case of integration of a constant. So integration of a constant, the equation will be of this form. So here it is y is equal to 5 or f of x is equal to 5. So we are added the Riemann integration strips. So here this is delta x, this is delta x, and this is delta x. And we can observe that delta y is 0 because lines are horizontal. So we will not be having delta y. And here I can write, so the general form is y is equal to k, and dy by dx is 0. And I can write delta y by delta x is 0. Delta x is not 0, so delta y is 0. Already we have told that delta y is the representative of the slope, so delta y is proportional to dy by dx, which is represented by k. So in this case, all these values, delta y, dy by dx, and k, everything is equal to 0. Here we may not be understanding it in a graphical form. Maybe in the next discussion we will understand in the graphical form. Here we may not be understanding in the graphical form. Maybe in the next discussion, in the differentiation of a linear function, we will be understanding in a better way visually. So we will consider the case of integration of a linear function. So integration of a linear function will be of the form y is equal to kx. So this will be of the form of y is equal to kx. So we are discussing about the Riemann integration strips. So these are all the Riemann integration strips. So here we are going to discuss about the slope. We are not interested in Riemann integration strips. So that means we are interested on these portions where we find the slopes. So we find that delta y, this is delta x, and we find that delta y by delta x is constant. So that is what we observe. So we will try to write that. So first our curve is y is equal to kx. So dy by dx, we have it as k. So and k is constant. K is constant for our case. And we can consider the three different cases of k. So the first case is k is equal to 1. So first we can consider the case of k is equal to 1. So it means that delta y by delta x, this is equal to 1. And so in other words, delta y will be equal to delta x. So here you can find that delta x will be equal to delta y. So that is why we are having the slope delta y by delta x is equal to 1. And here you can see that delta y by delta x is 1. Because the equation is y is equal to x, and this is a line passing through origin, making an angle of 45. So the slope will be equal to 1, and dy will be equal to dx. So that is what we observe here. Next, we can consider a case where k can be different value also. Okay. So for example, here the second case is k is less than 1. So for example, the equation can be of this form. So y is equal to 0.5 x. Okay, so when you find dy by dx, so this will be 0.5, this will be 0.5. Okay, and you find delta y by delta x, so this will be equal to 0.5. Okay, which is equal to k. And here you can find this is delta y, okay, this is delta y, and this is delta x, and you find that the delta y by delta x is approximately equal to 0.5. But in all the cases, you are finding that delta y is constant. Delta y is constant, and it is less than delta x. So that is what we observe in all the cases. Okay? Delta y is less than delta x, and it is constant for all values of delta x. Next, we will consider the case of k greater than 1 also. So when k is greater than 1, okay, when k is greater than 1, so then the equation will be of the form 1.5x, y is equal to 1.5x. So then dy by dx will be equal to 1.5, and I can write delta y by delta x will be 1.5, which is equal to k, and delta y by delta x, okay, this will be approximately equal to 1.5. And here you can find this is delta y and this is delta x, and the delta x is delta y is greater than delta x. Delta y is greater than delta x. So that is how we have k is greater than 1. And here also we observe though the k is greater than 1, delta y is greater than delta x. So the pattern is the same. Okay, so the pattern, that is the slope is constant. The slope is constant. So delta y is same throughout. This is the visualization which we have to drive with. So we have the three cases. Okay, so we have three cases for which the slope is given by delta y. For the first case, the delta y is equal to 1. The second case, the delta y is less than delta x. The third case, delta y is greater than delta x. Thus, for the three cases, we have delta y. So in this case, delta y is equal to delta x. So in this case, delta y is less than delta x. In this case, delta y is greater than delta x. For all these three cases, we find that delta y is proportional to dy by dx, which is proportional to k. So that is what we find it visually. So we can conclude that differentiation of the function y is equal to kx. It is constant, which is justified visually.